you would have a toxic ocean. And if you go back 1 million years or 10 million years or 1 billion years, it's so toxic. If you had a fish, it's a dead fish.
Yeah.
Too much nickel.
So what about some examples that we can actually see?
So examples that we can see. I'm going to use dinosaurs. And you say, well, we don't see dinosaurs today, but people have recorded in art, in oral history, in writing, with beautiful descriptions of what we now call dinosaurs. Now, the word dinosaur was not created until the 1600s. Prior to then, they were called dragons or other names in the local languages. But you can go to a church in the UK, there's a brass inlay which has got a dinosaur in there, along with other things that exist today, not fictional animals.
But dinosaurs are supposed to have died out 65 million years ago.
Yeah, that's what I was taught. That's what you were taught, and that's what most people are taught.
So how is this possible that we have these recreations and descriptions from
Because
humans?
they didn't die out 65 million years ago and people saw them and wrote them down. You can go to a church in Georgia. You've got carvings on there. You can go to Cambodia, Angkor Wat. There's a Stegosaurus there. One of the neat personal examples, my wife and I were holidaying a few years ago in the beautiful capital of Estonia, Tallinn. We're walking down a street, a narrow alleyway with centuries-old buildings either side of us with carvings in the stone. And I'm walking past and I go, there's a sauropod dinosaur carving in the wall, along with everything else that is real. It's not fictional. Take as another example. The Chinese years. You've got the year of the horse and the rat and the monkey and so on and so forth.
All these animals that exist today.
Yeah, 11 of them that all exist today. And nobody says they're fictional. And there's the year of the dragon. And the dragon is a description of a dinosaur. So why would we think that they slipped in one fictional one that they hadn't even seen?
Doesn't seem to make sense.
Doesn't make sense. So 11 real and 1 false, 12 real makes more sense. So these are observations that we make today.
So you're saying that dinosaurs didn't die out 65 million years ago. If we have all this evidence of connection with them and human beings, what about some other living examples?
Yeah, I'll talk about the complexity of living organisms. So even before you get to living, some of the complex molecules that are contained within living organisms are so mind-bogglingly complex, it is barely even possible to describe them. So take some simple peptides or proteins or polysaccharides or lipids or other complex chemical structures that are supposed to have formed by chance. And you look at the chemical thermodynamics, the probability theory, the chemistry that goes into the formation of these, they are so complex, it does not happen by chance. You can calculate the probabilities and it's off scale, 1 in a chance of 1 followed by thousands of zeros. That's classified mathematically as impossible. Complex organisms do not arrive by chance.
But it's the basis of their whole theory is that they are.
It is the basis of the whole theory, and that is what we're taught. But when you look at the empirical, historical, observational science, it does not stack up. Because I can measure the probability of combining 2 amino acids to make a dipeptide and 3 to make a tripeptide. But, by the time I'm getting up to 50 to make just a medium length protein, polypeptide, I'm now talking about probabilities that are less than 1 chance in the number of electrons in the universe. And this is science. This is thermodynamics. We learn this as undergraduates in school, and in some schools you even learn a little bit about it in high school. This is firm foundation science. You can measure the probabilities. Even under the most perfect primordial soup, you cannot form these complex molecules.
I feel like this complexity is all around us. As you say, we learn it at high school, we see it. Can you give us some other examples of this?
Yeah, and I've barely even got to the surface of it, but this is one thing that is really neat, and it was part of my PhD. There are some molecules that are called optically active. Let me explain that. It's a bit like our hands. I get a left hand, I get a thumb, index finger, and so forth through to my little finger.
Yeah.
And I got a right hand, thumb, index finger through to my little finger. So they're not the same though, because I can't put them on top of each other because they're not identical. They're mirror images.
Yep.
And a lot of biological molecules come in left hand and right hand. Now, when I, as a scientist, as a chemist, try to make molecules which are optically active. They come in left and right-handed forms. When I make them from simple chemicals, I get a 50-50 mixture because their chemical properties are identical. Same boiling point, same solubility. I'll get technical. Same dipole moment, same bond angles. Everything's the same. They're just mirror images of each other. So I end up with a 50-50 mixture. Okay, boring, Stephen. What's the significance of that?
Yeah.
Biological systems, proteins made of amino acids, where the amino acids are optically active, they're all left-handed. You don't find right-handed ones in there. So in this 50 amino acid polypeptide, they're all left-handed. There's
How
no
do you
right-handed.
know they're left-handed?
Because you can measure it.
Okay.
Yeah, this is testable, observable, measurable.
Yeah.
The rotation of the plane polarized light rotates it left-handed. This is getting technical, but you can measure it. People don't need to understand it. You can measure left and right-handed molecules.
Okay.
Now, this polypeptide, 50 left-handed ones. If I substitute a right-handed one in there, it becomes dysfunctional. It doesn't work as well, or in many cases will actually kill the organism because it doesn't fold the right way, it doesn't react the same way. It's just like I can't put my left hand into a right-handed glove. It won't fit. It's the same. You put a right-handed amino acid in there, it no longer fits.
Yep.
It doesn't fold in the right way. So, I've got to twist my hands in another way. If I want my thumb on there, I got to do something really difficult.
Yep.
And it doesn't work in biological systems. So, how do you get only left-handed ones from this 50-50 mixture? We can't do that as scientists. The only way you can even get close to it is through carefully controlling the environment through a lot of complexity. This takes a designer, a supreme intellect, far greater